presenting this a little bit now. So this sounds really, really complicated, NMR spectroscopy, and it isn't. And you don't need to know, if you don't like your physics and you go switch straight off, don't worry about it. Spectroscopy means radiation like rainbows of light, and it's going through material. Okay, so material in this case is carbon containing compounds or organic compounds. That's all it is. So different materials, as we know, absorb different wavelengths of light. So we know that carbon dioxide and water absorb infrared radiation. Now, NMR means it's radio waves, and it's the nuclei of certain elements, the nucleus right in the center, that absorbs radio waves. Radio waves are much bigger. There's me going, radio waves are much bigger than little tiny infrared waves compared to radio waves. So it's radio waves being absorbed by nuclei. So don't be scared by the word nucleus. It's got nothing to do with nuclear power. It's to do with tiny nuclei in the middle of some atoms that absorb radiation. Now, they can only do this if they're submerged in a magnetic field, and the magnetic field causes the nucleus of some atoms to behave like a tiny bar magnet. And what we then do is pulse it with radio waves, and it absorbs the radio waves and it flips. So I'm not going to go into NMR. I want to go how it's used to determine where those atoms are. So I'm not going to look at this use of T. We'll do this later on. Okay, I'm not going to look at this because this is not important. Okay, what we're going to do is focus more on the different types of carbon atoms present in the molecule and something called chemical shifts. Okay, on your data sheets, and I'll attach another one later, you will see carbon-13, so only atoms with odd numbers of nucleons like hydrogen 1, fluorine 19, carbon-13, odd number of nucleons, have this property that can absorb radio waves when they're submerged in a magnetic field. And you can see that carbon atoms that are attached to very electronegative atoms like oxygen give out a much higher signal that we call a chemical shift. And this chemical shift is given the symbol delta, and it's measured in parts per million. Don't worry about that. Okay, I'm going to focus in what you need to worry about. So carbons that are attached to electronegative atoms are more exposed, so they give out a higher signal, a greater signal. So you can see this weird scale goes from a high number down to a low number. Okay, so let's have a look at two molecules, propan-1-ol and propan-2-ol. So what I'd like you to quickly do, and I can't see you doing it, obviously, is could you quickly sketch either propan-1-ol or propan-2-ol? I can't see you doing it, but I'm going to show you the next slide to see if you got it right. So could you sketch down propan-1-ol and propan-2-ol? And while you're sketching that down, if you beam radio waves at a sample of propan-1-ol while it's submerged in this magnetic field, and all the carbon atoms in there are sending out little signals. Okay, these carbon atoms are sending out little signals. So that's propan-1-ol. If you draw the full displayed structure of propan-1-ol, you will see that there are 3 carbon atoms, and it gives out 3 signals. And that is because each carbon atom, so hopefully you've drawn your propan-1-ol and hopefully you've drawn your propan-2-ol. Each carbon atom in propan-1-ol, this is this molecule here. So this molecule here, this carbon here is giving out a different signal to this carbon here and a different signal to this carbon here. And this is because this carbon is attached to an oxygen, so it's less shielded, so its nucleus is more exposed, so it's giving out a signal here. This carbon is giving out a different signal because it's not attached to an oxygen, and this one a different signal as well. We say, sorry, I need to go back. We say that these carbons are not equivalent. They're in completely different environments. Now, if we go to carbon, if we now go to propan-2-ol has got 3 carbons, but these two here are identical. They're in the same environment. We say they are equivalent. So this will give out 2 signals. So these 2 will give out the same signal, and this one little one here on his own that's attached to an OH will give out 2. So even though they're the same molecular formula, the 2 position isomers will give 2 different spectra. So we can distinguish between the 2 isomers using carbon-13 NMR. So let's now have a look at these 2 molecules here. And this here is 2-bromopropane. It's going to give 2 signals. And this molecule here is an ester. And the ester is methyl ethanoate. Let's see how those signals originate. So, this is going to give 2 signals because the carbon that's attached to the bromine is going to be more unshielded. Where would you get the data from? Your data sheet? And these 2 groups here are identical. So that's got 2 different carbon environments. Now, in our ester here, we can see we've got a carbon attached to an oxygen in this OCH3, and we've got another carbon attached to an oxygen here. Now, we need to go to a data sheet, but this has clearly got 3 different carbon environments. So let's have a look at, this one here, C3H6O. That can either be an aldehyde or a ketone. It can either be propanal or propanone. Propanal or propanone. And it's got 3 carbon signals. So if you draw the possible structures of C3H6O, it can either be propanal or propanone. So we've just been looking at aldehydes and ketones. Propanal has got 3 different carbon environments. And you can see here, this carbon that's attached to an oxygen is going to have a higher chemical shift because it's less shielded. But each carbon is different to the other. There are 3 non-equivalent carbons. But in propanone, carbon 1 and carbon 3 here are identical because they're both CH3s. That would only give 2 signals, and therefore it had to be propanal. Okay, so I'm going to quickly move to the more complicated thing, because this is what I'm going to ask you to do a little bit of research on in benzene. So we're going to be studying benzene after carbonyl compounds in a couple of weeks. So even if you do this research now or later, it will help you to understand the Cambridge Challenge a little bit better. These are isomers of CHH10. This circle here is called a benzene ring. And all a benzene ring is, this ring here is sometimes drawn in textbooks as 3 double bonds. And there was a chemist called Kekulé who proposed the structure of this weird unsaturated molecule, C6H6. So these all contain benzene. Nowadays, the Kekulé structure has been disproven. And a little bit of research that you might want to carry out is what evidence is it that it's not alternating single and double bonds. In fact, the 6 electrons are delocalized in this benzene ring. Now, these structures here are dimethylbenzenes. So this structure here is 1,1-dimethylbenzene. And this structure here is 1,3-dimethylbenzene. And this here is 1,4-dimethylbenzene. And this structure here is ethylbenzene. And what you need to be able to do is to predict how many different carbon environments there are in each of those isomers. So think about it on a piece of paper. I mean, this slide is actually telling you that this would give 4 different carbon environments. And I'm going to walk you through them. This carbon here, what you do is you draw a line of symmetry through it. So we draw a line. The more symmetrical your molecule is, the fewer carbon environments they're going to be. So this is mirrored with that. So these 2 carbons here, carbon 1s, are equivalent. These carbon 2s are equivalent. They're exactly the same because they've got a carbon 1 attached to them, which has got a carbon 4 coming off it, which has got a methyl group. So this molecule here has 4 different carbon environments. Whereas if we go to 1,4-dimethylbenzene, it's only got 3 because it's the most symmetrical. If we put a line through here and a line through here, carbon 1 is mirrored with carbon 1 here. These 2 are equivalent. Carbon 2 is equivalent to carbon 2s here. They're equivalent. And carbon 3s are equivalent. So that has only got 3, that would only have 3 peaks in its carbon NMR spectrum. Whereas this molecule here, ethylbenzene, will have 6 different environments. The best way to do this is to draw out the full structures rather than the skeletal structures, and you might be able to see it a bit clearly. Right, here is now the stretch and challenge bit. This is the stretch and challenge bit I'm going to talk to you about. So I'm just going to go back to you guys. Can you still hear me? Just someone type in yes, you can still hear me. Thanks, Dan. So Dan's still awake and paying attention. Right, wake up. You can take your phones out of your pockets now. So I'm now going to show you the little quiz bit. On Google Classroom, I have, on week 5, above today, the live lesson, I put carbon 13 NMR stretch and challenge as a quizzes. You can also see it on the screen. I shall move it to the top. Okay, so you can see it. So here's your little challenge. It's 1 question. Right, so I'm going to walk you through the question. Right, so there's the link. And I'm going to show you the question now. Okay. Right, so this molecule actually does exist. It was created when chemists were having a little bit of fun. It actually doesn't serve much purpose. But when we're looking at nanomolecules, we can now build little nano machines. So these are called nanodancers, and you might recognize it in college in the Costello Theatre. So I gave them this design. I didn't design it, I'd like to say I did. And each carbon, you can see here, so each carbon in the skeleton, so there's 1 carbon, there's 1 carbon, there's another. So each carbon has its own environment. So you could see that that carbon there and that carbon there might be equivalent, they're the same. So what I want you to go away and do is I want you to try and work out how many carbons, how many different equivalent carbons are in the nanoputian. And then all you need to do is type in your answer and submit. You don't have to do it this minute. I'm not expecting you to do it during the live lesson. So that's your little stretch and challenge. It's only 1 answer quiz. So you just fill in the blank, put down your number. Just don't put a number in, don't put any atoms or anything, just put a number in. Okay. So each of these, so that thing there is a benzene ring. So you can see the benzene ring drawn now has got alternating single and double bonds. That's called the Kekulé structure. The benzene that we see in A level is drawn with a circle in it, but this is just so you can see equivalent carbon atoms. Okay, so that quiz is on Classroom now.